Okay, what we're going to do is we're going to pick up where we left off. We're going to be talking about Chapter 18, the cardiovascular system, which is the heart. And it doesn't take very long. We're going to go through the heart. We're not covering the physiology of the heart. We're just talking about the anatomy of the heart. So it won't take very long for us to get through this portion of the discussion.
But because we like the Packers, we don't like other teams.
Let's go ahead and grab the PowerPoint here, and we'll get started.
So we're like anti-Bears, for example. Okay? Anti-Bears. We love the Packers, but we're anti-Bears.
All right, so
if we had a Bears player,
we already know where the heart is. If before you even walked into class here, you know what the heart is. You know where the heart is located. So we're not going to really discuss that. But when we look at the heart itself, remember we talked about how there are serous membranes in the body, and I gave you the example of taking a balloon and putting it in your hand, and the balloon is resting on your hand, and that part of the balloon that's touching your hand is the parietal layer of the serous membrane. And then if you take your fist and you push it into that balloon, then the balloon that's touching your fist is going to be the serous layer. And so that's what we see here in the heart. But let's start first of all with this layer in this part of the heart. This is the inside of the heart. And the inside of the heart is lined with a lining called the endocardium. The endocardium is smooth. It's like Teflon. It's non-stick. And the endocardium is going to be continuous with something called the endothelium.
So the reason why this is significant is
of the blood vessel, when we get to the blood vessels in the next chapter. So the endocardium is the innermost layer. The middle layer is called the myocardium, and that's the muscular layer. This is the thickest layer. This is the part of the heart that contracts, which is the pumping part of the heart, the muscular layer. And then we have an outer layer called the epicardium. The epicardium is actually the equivalent of the serous layer of that serous membrane. I'm sorry, the visceral layer of the serous membrane, the visceral layer. Remember, we have a visceral and a parietal layer. So the visceral layer, as you can see, is directly attached to the heart. It is actually a layer of the heart, just like that balloon is touching your fist. But then remember that part of the balloon is going to eventually loop around, because the balloon is a sac, and then you're going to loop around to this way. And so this other layer here is the parietal layer of the serous pericardium. And in between we have a cavity here which is filled with a fluid. It's like a lubricant, and that lubricant protects the heart. So the heart is basically surrounded by this cushion of fluid, and it prevents the heart from suffering damage due to rubbing up against structures that are in the general vicinity. Your heart is going to contract 60 to 80 times per minute, and so you don't want your heart rubbing up against the external structures to it 60 to 80 times per minute. Now, the heart is a very sophisticated structure. It looks very simple, but if you were to try to, and doctors have tried to, and scientists have tried to, and multiple people have tried to create something that works as well as a human heart, because the human heart has its faults, it has its defects, so it's something that breaks down. So wouldn't it be nice if we could make a mechanical version of a heart that would do the same thing? Well, we can try, but number one, the heart is extremely compact, and it's hard for it to do that. So the heart cannot, we cannot create a version of the heart that fits in the same space that does the same thing that a heart does. The closest thing we have is something that's about the same size as the heart, fits in the chest, but it's a temporary arrangement, because they have to walk around with this device with tubes out of it that keeps it going. So it's not a very mobile thing. You can't just go up and everywhere, and also it's not going to accommodate for changes in physical activity either. So it's a remarkable structure, but it's a pump, and it basically brings blood into itself. It sucks the blood into itself and then pumps it out to the body. And so what you're going to see is that the heart is broken up into actually two regions. Two, upper region and a lower region. And so when the upper region is contracting, it's squeezing the blood into the lower regions. And then once the lower region contracts, it's going to push the blood out through the blood vessels
the antibodies.
while the top is relaxed, allowing more blood to fill in. And so as the blood fills into this chamber, then this one will relax, and then when that relaxes, this one will squeeze the blood back down into the lower chamber, and the whole thing happens again. So it's top, bottom, top, bottom, top, bottom, top, bottom, as far as contractions are concerned.
Appropriate blood donor level.
The third term is the term myocardium.
So if you enjoy that. Here's another term, I'm sorry, another term here that I don't want you to forget it, don't want you to miss it. Out of my screen share. Oh, did I not share this? Oh.
Here we are. So this is the external structures of the heart.
For today is the
So
term.
what we can see are some of the great vessels associated with the heart.
Second term.
The blood is returning from the body and coming to the heart through two main veins called the vena cava, the superior and inferior vena cava.
Okay, so that takes us through the end of chapter.
We also have blood leaving the heart to go to the
Back.
lungs, to what we call the pulmonary trunk, which then branches into the right and left pulmonary arteries. So carry the blood to the lungs. Then the blood returns from the lungs through the right and left pulmonary veins. And then the blood will leave the heart and go to the systemic circulation and the rest of the body through the aorta, which is this large red blood vessel you see here. All right, a couple other things. We've got these structures right
All
here.
right. So today
These
we're
are
gonna
called
be talking-
auricles.
We're going to be talking about
Auricles
Learning Plan 11. Learning
refers
Plan
to an
11, actually,
ear.
we're gonna cover
So it's like an
two-
ear flap
So today we're going to cover the first
of
two
the atria. The
Learning
atria
Plan
are like the
11.
openings. Like if you go into an atrium of a building, it's the first thing you come into.
Then we're gonna move on
So
to
this
chapter
is like the
18.
this is like the heart, the atrium of the heart. You have two of them, left and right, and the auricles can expand to accommodate an extra amount of blood if necessary. So when blood is entering the atria, if there's a little bit extra or that we need a little extra space, the auricles can fill with blood. We also have these blood vessels here. You can see blood vessels along the front and the back sides of the heart. This is the coronary circulation. We probably hear of a coronary from the phrase loosely said, don't have a coronary. And what they mean is don't have a heart attack, right? Don't get all upset, don't have a heart attack. Well, the coronary circulation is the circulation that actually feeds the heart itself. So if you think about what the role of blood is, we talked about the role of blood. It's a transporter, right? Transports gases and nutrients to the other tissues of the body. Well, the heart has to feed itself. And so the coronary circulation is the way by which the heart feeds itself.
And when we talk about blood, remember that blood.
However, if you do get a blockage in the coronary artery, so you get a blockage here, now whatever is distal to that blockage is going to be deprived of oxygen and nutrients. So then you'd give that person a bypass where you actually bypass the blockage so the blood can get around and still allow that area to be,
So it's the characteristics and qualities of
to get the oxygen and nutrients that it needs to. So that's the coronary circulation. It's the circulation of the heart that actually feeds itself. It's the way that the heart stays alive.
So we're going to see.
Looking at the backside, you can see the coronary circulation again. You can see the blood from the coronary circulation returns through the coronary veins. The large vein is called the coronary sinus. When we see this term sinus here in the cardiovascular system, that just means a large dilated vein. All right, so here's the inferior vena cava again. The superior vena cava, the pulmonary trunk is going to divide off into the left and right pulmonary arteries. The blood comes back through the left and right pulmonary veins, which we see, and then here's the aorta. So just what we saw before, just a different view. If we cut away the front of the heart, now we see the chambers of the heart. We see that we have two chambers here, 1, 2, and then we have another 2 chambers here, 3 and 4. So chambers 1 and 2, which you see are called atria together, but the singular is atrium. We have a right atrium and a left atrium.
See at the bottom that you get.
And then the bottom 2, chambers 3 and 4, are called ventricles. We have a right ventricle and we have a left ventricle.
You've got a really
So,
thin layer.
let's just follow the order in which blood passes through the heart so we can understand the flow of blood. So blood is going to return from the body through either the superior or inferior vena cava. If it's returning from above the heart, from like the head and the upper extremities. Then it's going to be coming back through the superior vena cava. It's coming from structures below the heart. It will come in through the inferior vena cava.
Blood that you're donating. You're donating.
So the vena cava are going to dump into chamber number 1,
This is where all
the right ventricle.
Like,
I'm sorry, back up. Shoot,
Just
the right
remember
atrium.
gases that are
Getting ahead of myself.
red blood cells.
Then the blood will be pushed.
Some gases.
When the right atrium contracts, it'll push the blood down into chamber 3 here, which is the right
Then this middle layer
ventricle.
here, we call it the Buffy coat.
So right
Where
atrium,
you see your
right
white
ventricle.
blood cells.
Then the next step is that the blood is going to exit the right
Slow down
ventricle, and it's going to exit the pulmonary trunk
your blood vessel.
by way of the right and left pulmonary arteries. So the pulmonary trunk is number 3.
Agent. Then the leukocytes.
Then blood is going to return from the right
in trying to
and left
neutralize the
pulmonary veins.
at least one of your body's approaches.
It's number
So
4.
we can see that we have really.
And that blood will dump into
red blood cells,
the left
the white
atrium.
blood-
So that's step number 5.
The white blood cells, and then
So
we have
blood
the
returns to the left atrium. Now it's nice and
Maybe hard for you
oxygenated
to
from
see
the
if you're
lungs,
looking at
because
this
that's why it
slide.
went to the lungs in the first place.
here today
become
in class, or if
oxygenated.
you're watching the replay,
Then when the
turn
left
this-
atrium contracts, it pushes blood down into the
You'll
4th
see
and final
a list of the things that are found in plasma.
chamber, which is the left ventricle. So that's step number 6 along the way.
Here about
And then the left ventricle will contract and push blood out the aorta, which is our final stop.
when we talk
And the
about
blood will
the
leave
blood,
the heart through the aorta and provide the body with oxygen and nutrients. So that's the flow which blood passes through the heart and other structures. Right atrium, right ventricle, the pulmonary trunk. Then it returns through the right and left pulmonary veins into the left atrium, then the left ventricle, and then the aorta.
About 8% of the weight of the plasma volume.
Now we have valves that prevent the backflow of blood, because if you've got the heart here, you've got the 2 chambers on top and 2 chambers on the bottom, you want the blood to go from the atria into the ventricles. And so you have valves which allow for the blood to flow one way.
Egg whites. Albumin is really
All right, I'm gonna get rid of those
helps
So I
regulate
can
your
continue to draw on this. All right,
whether the fluid
so you have a valve.
is
So when the blood wants to go from the atrium to the ventricle, you want that valve to open up and allow the blood to pass into that valve. But when the right ventricle starts to contract, it wants to push the blood back where it came from. And you can't have that. You can't have blood going back into the atrium.
we get to advanced AMP,
So what you need to do
osmotic pressure and osmotic
is you
gradient.
need to have a valve.
How the kids-
It's a one-way valve.
That'll make more sense.
So that way,
For now,
it only
let's
opens
understand the
one
level
way
of, hey, this is where the
and
fluid
doesn't
is.
allow for the blood
Either
to
in the
pass through.
plasma
So
or
you
out of the
want,
plasma.
so let's say this is the,
Or out of the blood. That's
this
okay.
is the valve. You want it to
The
go
next one
down,
we see,
but then when it's, when it
certain
comes up, you want it to close
36%
shut
proteins are called globulin.
again. So you want this to come back and close shut. You
Or,
don't want it
as we
to
call
go up this way,
immuno-
because then the blood will pass back through. This is called a prolapse. So we have some structures in place to help keeping that from happening. But here are the valves. We have 2 that are atrioventricular valves. So from our point of view, we are in the atria. We are the atria.
Those are
So blood going into the screen, into your picture, is going into the ventricles. We have one with 3 cusps. That's called the tricuspid valve. And then we have this one, which is a bicuspid, which is the mitral valve. We hear the mitral valve a lot because the mitral valve has to withstand a lot of back pressure. That left ventricle is really squeezing, and it really wants to push that blood, and that blood really wants to go back where it came from through the mitral valve back into the left atrium, and the mitral valve has to withstand that. So if the mitral valve is compromised, it's weak, it's ineffective, then we can have what's called mitral valve prolapse, which is what we talked about right here.
And when you suffer an injury,
Then we have 2
your blood-
valves that are coming toward
what
us.
happens is
So the
you
blood
have
that's
a
leaving
cascade
the left
of
ventricle
events that occur
will pass through
above
the
that stage.
aortic
When you
valve.
form a blood
Blood that's
clot.
leaving the right ventricle
So
toward the
what happens
lungs is going to pass through the pulmonary valve.
It gets converted into something called fibrin.
So as I mentioned, you have some structures that help prevent prolapse. So you can see you've got these cord-like structures that are going to attach to the valve. These are called chordae tendineae, kind of like ropes that are attached to the flap so that the flap doesn't prolapse. So you don't want the flap to prolapse, so you've got these ropes that are attached to the valves and are holding on for dear life. But then you've got this muscle right here, looks kind of like a finger, and that muscle is going to pull down, contract, to pull down on these valves to keep the valves from prolapsing, to keep that valve shut. Okay, so we have the papillary muscles pulling on the chordae tendineae, which pull on the valves to keep the valve from prolapsing. There's a picture in your book that shows you the circuit of blood through the heart. You can refer to that if you want to or need to.
You look at
So when blood passes through the heart and it leaves the heart to go to the lungs to get oxygenated, we call that the pulmonary circuit.
most of what you see.
Then when the blood returns to the heart and then gets pumped through the aorta to provide blood to the rest of the body, we call that the systemic circuit. And we'll talk about those circuits when we come back and talk about the blood vessels. You'll notice, and what this picture is trying to show you here, is that the wall of the left ventricle is much thicker than the wall of the right ventricle. And that's because the left ventricle has to overcome the back pressure of the systemic circulation. It requires a significant amount of pressure to get blood out of the heart into the rest of the body. Whereas the left ventricle only has to overcome the resistance to flow that exists within the lungs. So the wall of the right ventricle is much thinner than the wall of the left ventricle.
You're technically donating.
We already talked about the coronary circulation, so we don't have to talk about that.
Everything. You're just basically sticking
I'm going backwards here.
pulling out the blood, and then it goes.
And then finally, the last thing is just a review of the histology of cardiac muscle tissue. Remember, this is something that you saw in Learning Plan 4. 3 different types of muscle. One of the 3 was cardiac muscle tissue. Cardiac muscle tissue is striated. It's short. It's branched. You have the intercalated discs that delineate or mark where the muscle cells come together and join.
The red blood cell of that.
Just like we saw in skeletal muscle, we have the A bands, the I bands, the light band, the dark band. We have the Z disc, thick and thin filaments, the whole 9 yards. We've got that all there. It's just that it looks a little different because cardiac muscle tissue is short and branched rather than long and cylindrical. Another unique feature of the heart is that you have these gap junctions, which allows the heart to contract much more quickly and as a unit. So if you recall, when we talked about, we were in Learning Plan 9, what we did is we talked about the action potential. So you have the nerve, axon, and then you have the axon terminal. So the action potential passed through the axon, and then we had the release of neurotransmitter into the synaptic cleft, right? And then that neurotransmitter had to bind to a ligand-gated channel to open it up to allow sodium to pass through. And if we had enough sodium passing through, then we'd have a rise in the membrane potential, hopefully to minus 55, and then we get an action potential, right? So that takes a lot of time. When you're talking milliseconds, it takes a long time. So the heart doesn't do that. From heart cell to heart cell, we have these direct connections, these gap junctions. And so what happens is the sodium ions are just going to flow directly from one cell to the other, and that causes a much more rapid change in the membrane potential, which allows for a quicker action potential, which equals a contraction. So the cardiac muscle cell fibers contract as a unit, as a whole. When one contracts, the next one contracts right along with it. And that's what you want. You want your heart contracting as a unit.
And some of those parts will be recycled.
And we'll talk more about that when we get to advanced A&P and talk about the physiology of the heart
Carry respiratory gas
and the cardiovascular system itself.
So they don't have organelles there to take up.
All right, my friends, so that is it. That's all we have to cover here. So that was a relatively short presentation, but thank you very much. And the next time we get together, we come together, we will be finishing up Learning Plan 11. We will move on to Chapter 19, which is covering the blood vessels. And then we'll finish off with Chapter 20, talking about the lymphatic system and so forth. Thanks a lot. Take care.
Or the alpha globin proteins that were in plasma. Okay, well, we've got, and the beta. So we